Okay, kitty, kitty, kitty. Alrighty. So, back into the mess that is kinetics. This will be very exciting, I'm sure. Um, let's talk a second about what or how to kind of easily tell what your reaction order is going to be, or specifically reaction order with respect to a particular reactant. There's kind of an easy way to do it. Most reactions are going to kind of fall under one of two categories. They're going to be, or rather, two out of three, but most of them will either be first order or second order. And so I've thrown out the integrated rate laws for those particular scenarios. So the first order on the left with the natural log, the second order with the inverse. Notice that both of these follow the kind of slope intercept line formula, right? So it turns out that if you graph your data, then that means you're going to see whichever one is linear is the reaction order. Let's go ahead and take a look at what that means. So, two graphs here. The first one, let's do a first order reaction, or rather, we'll graph the data as if it were first order. So we're going to have the natural log of our concentration at a particular time, and then we're going to have our x, of course, will be just the time. Same thing here, we're going to have 1 over a at given time. And so we're going to see that, hey, if your natural log one looks like this, but your inverse one looks linear, then that tells us that this reaction is second order. So one thing that we would do in the lab, again, something we can't do here, is you would be basically collecting data of concentration over time as a reaction is happening. And you would end up with, a table that would say, okay, here's our time intervals, whatever those might be. And, you would end up with your concentration of mystery reactant, right? So these would be the data you collect, whatever they happen to be. So, maybe every 30 seconds you're taking a measurement, or every 2 minutes you're taking a measurement of something. And so what you would do is then you would also figure out what the natural log of A is, as well as the inverse of the concentration of A. You would end up calculating these two. And you would end up graphing all three of these versus time. So your first graph would be just concentration versus time. You would then graph the natural log versus time. And then you would also do the inverse versus time. And whichever one ends up being linear, that's going to be the one that your reaction order will be. So depending, as you can see here, I've written kind of 0, 1, 2. If this one is linear, it's second order. If the natural log one is linear, it'll be first order. And then one we haven't talked about yet is zero order, where there is not a concentration dependence in your reaction. So just remember that if you were to have these particular reactions, you would say that rate is K times A for a first order. If it's a second order reaction, it would be Ka squared, right? These are all in respect to one unit, by the way. So, or one reactant. So if you have multiple reactants, you would end up doing these graphs for all the different ones that you're changing, and you'd be able to figure out what the reaction order is in respect to each reactant, and then you can do overall. One that's zero order does not actually have a dependence on concentration. These are a bit less common, but they do exist, where something is just happen at a steady rate continuously. There's no concentration dependence on it. Interestingly enough, metabolism of alcohol is a zero order reaction, which means that, once you take your first sip of beer or whatever, your body is going to be decomposing that alcohol at exactly the same rate. So even if you, pound, a bunch of shots or something in a short amount of time, your body is still going to be, digesting it at the same rate as if you were to, do it over, like keep drinking beers over time or something. So, that's a fun fact there. However, if it were first order or whatever, your body would digest it faster if you were to binge drink otherwise. So no concentration dependence for a zero order reaction. Let's see. I guess we can throw out, I don't think we haven't done an integrated rate law for zero, have we? Let's just do that real quick. If we were to have a zero order reaction, we would just see that the concentration would be equal, just simple, plain old, no fancy things to deal with here. So we just have, again, we have y equals mx plus b. Y does not have any dependence on concentration. It's just your plain old concentration versus time. Pretty boring. Not as common as first or second order reactions, so we're going to kind of focus on those two a little bit more. So, cool. So if you're given data, which hint on your homework, you will be given data, and on your exam too, I guess I can throw that out there. You're going to want to make sure you're comfortable graphing all these things. So I would recommend kind of using something like Excel to do this for you, where you can just take your data, whatever it happens to be, these little dots, and give it the formulas to do the natural log and the inverse of those, and calculate those for you real quick, and then graph them. You can do all of those versus time, and choose whichever one is linear. And interestingly enough, once you figure out which one is linear, then you can do all those fun calculations. You can figure out what k is. That's going to be your slope, right? And so if you use Excel to figure out the formula of your graph, you can figure out k very easily that way. So that's a hint for you on your exam. Maybe be familiar with that. It's going to save you some time. Our exam is still a couple weeks away, so don't worry about it, but this will definitely help you on the homework. If you do it on the homework, by the way, just like write, I did this on Excel, and this is the equation I got out or whatever. You don't have to manually do it if you don't want to. Cool. So that would be kind of the easiest way if you have no idea, what your reaction order is going to be. This is a kind of easy way to do it. And so we're going to see today how these factor into what is actually happening in reactions. So cool. Any questions on the kind of this thing so far? These three different orders of reaction? Okay. Well, I kind of want to give you an example, but I think it would take too long. So maybe what I'll do, I'll just post some videos of how to do this sort of thing on Excel. Actually, maybe I do have Excel here. Well, you know what? Let's just do it tomorrow. Then I'll have it prepared because I don't want to spend all this time putting in data. So we'll look at that tomorrow. I'll show you how to do that since we don't actually have a lab class. A is just whatever your substance is that you're looking at. So if it's nitrogen dioxide, like we've done in that, it could be whatever substance. A is just generic substance. So yeah, we'll do that tomorrow. We'll work with Excel on that. So cool. Alrighty, cool. Any other questions on that? Alrighty. Well, in that case, let's go ahead and pop back into those graphs we kind of talked about towards the end of Wednesday. I remember we had kind of something like this, where we had kind of a reaction progress and energy type of graph. We saw that there were a couple of interesting kind of components on there. We saw that this one was the activation energy for the reaction. And that's kind of, the spark that's needed to get stuff going. It's the energy required to reach the transition state. And so that's going to be something that, remember, we saw that, a certain proportion of molecules at a given temperature will have that energy to be able to react. And by messing with the temperature, we can have more of those molecules having enough energy to react. We can actually, there's an equation that's going to be able to relate kind of our reaction rates idea to this activation energy. And that's called the Arrhenius Equation. You don't need to memorize the name, of course, but this is the Arrhenius Equation. It's relating. By the way, A is used here, unfortunately. That is not the same thing as the A that we just talked about. Here's our activation energy. And so we can see here how it's going to relate to the temperature component. And of course, we have our dear best friend, our gas constant R, as always. E being the mathematical constant there. What's interesting here is we have this A term. A is called the frequency factor. This is not the same thing as concentration of A. And this thing is going to be interesting because it is temperature independent. So we're going to see that temperature is going to mess with our activation energy. That's why it's kind of grouped up there. But A is actually going to not really interfere temperature-wise. There is actually a small dependence of temperature, but it is so small compared to the activation energy related to temperature that we kind of just consider it constant. So we're not going to worry about A as much. If we mess around with this mathematically, aka just take the natural log of this thing, we're going to see that the natural log of our rate constant, let's see, what am I missing here? Oh, natural log of A, of course. If we mess with this equation, guess what we can do with it? Lo and behold, are we seeing a pattern here? we can mess with all of these fun equations to get them into some sort of linear form. And so we would use this whole kind of chapter is a mess of equation. It's kind of like, when the heck do we use these? This particular equation can do two things. We can use it, first of all, to calculate the activation energy for a reaction. Or we can use it to calculate the rate constant at different temperatures. So we're going to see here, those are going to be the important components that we're going to get out of this reaction. So notice here we can mess with two things. We have our slope term, which will give us EA, our activation energy, and we have our temperature term. So I'm sorry, we have our K term. That's the other one we're working with. So those are kind of the two big components we're going to get out if we can graph this thing. Allow me to do some more mathematics. Or I'll derive the equation for you. All right, if you don't like deriving equations and you just want the product, close your eyes for 3 minutes. If we solve this equation for natural log of A, remember A is going to be temperature independent, we're going to get natural log of K plus EA over R times 1 over temperature. Notice that this would be at whatever temperature we want, and we would have a particular K at that temperature. Notice it's also the same as the since ln A does not have a temperature dependence, we could see that it's also equal to the natural log of a different rate constant at a different temperature. Remember, rate constant depends on temperature. Throwing this all together, we can say that natural log of K1 minus natural log of K2 equals EA over R times 1 over, I hate deriving equations, but some people like to see it. Best moving things to different sides. Remember that natural logs, when they're subtracted, is the same as dividing the... Oh my gosh, it's so ugly. We can see those are going to be there. Equals EA over R times 1 over T2 minus 1 over T1. Great. Now we can see, how exciting, we can see how to figure out different Ks at different temperatures. Honestly, I kind of like the first one better, but whatever, this works. You can use this form for determining K at different temperatures. So kind of, honestly, I'm going to just keep it as, it's not, okay. That's going to be kind of one equation that you'll work with. And the other one, I would keep it as this one. If you want to just find EA, use this one. It'll be a little easier. If you want, use for calculating EA. We're going to do both of these. How exciting, in an example. But I would use this equation here for determining K at different temperatures. I would use that first equation for determining activation energy. So, good news. I actually spent Sunday, while you guys were relentlessly doing the massive homework assignment I gave you, instead of doing the homework assignment myself, which I'll do later, I spent it actually looking up examples for you guys. So we're going to make sure that we don't have any more snafus in this kinetics stuff. So I have like 4 different textbooks here that are going to have examples for me. So I have one for us. Let's go ahead and figure this out. So if we know that the natural log is going to be negative EA over R 1 over T plus ln A, we can figure out what EA is going to be, right? Negative EA over R is our slope, right? Which is going to be change in Y over change in X. Just mathematics, how that works. So that would be the change in ln K over the change in 1 over T, which would be ln K2 minus ln of K1. Doesn't kinetics just make you sad? If we have all this information, which I have here, let's. I'm gonna just give you 2 points on this particular on this graph that's in one of the books. Is this the book that we use for you guys? No, but suffice it to say, at T1 at 300 degrees Kelvin, not degrees, that's Kelvin, ln of K is equal to 23.216. And at temperature 2 at 325 K Kelvin, the ln of K is going to be 23.539. Just copying stuff out of a giant table. Hooray, we love giant tables. And we can go ahead and figure this stuff out. If we wanted to figure out the activation energy, we can plug this fun stuff in. Again, you can just graph these, plug it in, and get your slope. That would be EA over R. But if we're doing this manually, we would just do this part. So if we do that, we're going to see that negative EA over R is going to be equal to 23.539 minus 23.216. No units because those are natural logs. 1 over 325 minus 1 over 300. Doing this, I don't know why I just closed the book because now I actually have to do the math. Let's do it. All right, so 23.539. Go ahead, Kevin, do it also. 216. That divided by parentheses. I guess we'll need multiple parentheses here. 1 over 300. I hope I got the right answer. That's going to be 90,565. What did I do wrong, Kevin? Oh, I see. I forgot a parenthesis. You're absolutely right. I forgot. I made all this, rambling about parentheses, and I didn't even put them on mine. Yeah, I get 1260. Absolutely. Awesome. So we get negative 1259.7, which we would technically round if we wanted to finish the problem here, but we're not going to. So notice that this is going to be in units of, let's see, we have, this will be in Kelvin, right? So, yeah, that's Kelvin. if we look at R, remember that R is we had this, value of R, or we also have the corresponding one in joules, right? Typically with activation energy, we're going to want to deal with joules rather than liters times atmospheres. We don't really need to worry about pressure and volume units here. So if we plug this in, negative EA, let's just say EA, equals negative R times all that crap, negative 1259.7 with 3 sig figs, is going to be equal to 8.314 joules per Kelvin mole times 1259.7 Kelvin. Notice Kelvin cancels out. We do this math, and we get, Kevin, if you would be so kind. Actually, I have this already set up here. I can do it. Times 8.314. Hooray. We do this, we get 10,473 joules per mole. Hooray! I'm glad we can do math. Well, you guys can do math. I can't, apparently. We should throw in our sig figs here. It looks like we had 3 sig figs to deal with, so let's just go ahead and round this accordingly. We would have that answer, or if we wanted, we could say 10.5 kilojoules per mole. That would be the energy to do that reaction. I'm rounding up, Kevin, but depending on what you had, you may need to round down. So, cool. Hooray! We are able to figure out the activation energy for a reaction. Notice that activation energy is just kilojoules per mole, so it depends on how many moles you're having. That's going to be the amount of energy required to get all of those over that hump. There's no temperature component for activation energy. That's going to be a constant, that you would use, for a particular reaction. Cool. So, any questions on that one? If you're doing this graphically, oh, I hope I didn't just get rid of the note. I hope not. Please. Oh, thank goodness it's saved. Ooh, that was scary. Okay. No, I do not want to type on this. I want to draw pretty lines. Oh my gosh. There we go. Sorry about that. That scared me. Let's just go ahead and save this again just in case. We don't want any more problems. Oh my gosh, I have to do this all over again. Okay. Here we go. Sorry. If you're doing graphically, remember that your slope is going to be negative EA over 8.314 joules per mole times Kelvin. So whatever slope you get, just use that. So that would be from Excel. And then you can calculate EA that way as well. All right. Cool. Any questions on that one? Alrighty, so in that case, let's go ahead and do one for the second equation here. Let's say that we had maybe it'll probably make things faster for you. I would suggest doing it. We'll go over it tomorrow anyway, so there shouldn't be any kind of problems with it. You can get Excel for free from the college, so That shouldn't be a thing. If you just go to like Office 365 and just put in your student email, they should give you Excel for free. So that'll kind of be the fastest way to do this sort of thing. If you're an Apple user, I'm sure whatever the Apple equivalent is will work just fine. I don't quite know exactly how to use it, so you'll kind of just have to YouTube some like how to do this stuff in whatever the Excel equivalent is. So yeah, cool. You could also just use like Google Sheets too. It should work. Anyways, that aside, let's say now we had that same problem. Let's go ahead and see what if we can figure out what the second rate constant will be at a different temperature. So I forgot what our first one was. LNK1 was 23.216. Okay. We can figure out what our rate constant will be at a higher temperature using the second equation there. So we saw that the ln K1 minus ln K2 was equal to EA over R times 1 over T2 minus 1 over T1. I hope I copied that correctly. Let's see here. Did I? Yes, I did. Okay, good. So with this in mind, we can figure out what K2 is going to be. So if we just plug in the numbers that we have, we've already calculated EA for this reaction to be, let's just keep 10,473 for now. That was joules per mole. We have 23.216 minus natural log of K2 would be equal to 10,473 over 8.314 times 1 over 350 minus 1 over 300. I'm omitting the units. I hope that's okay, because we're going to have a natural log anyway, so it's not going to have units, so everything should cancel out here. But let's go ahead and do that. So 10,473 divided by 8.314 times 1 over 350 minus 1 over 300. Hopefully this one I can do correctly. Yes, I got something reasonable for once. $0.5998. 5, let's say. Solving for ln K2. Add this number to 23.216. I get 23.816. And if we solve for K2, that's just going to be e to the 23.816, which is going to be some crazy big number. But that's okay. This is a particularly fast reaction, it seems. E to the 23.816. Oh my gosh, we get 2.20 times 10 to the let's see, what is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the 10th. Wow, how exciting. And this would be awesome. And that would be meters molar per second, or per molar per second, or whatever it happens to be. Or I guess this is actually per molar per second, huh? Let's not worry about the units, actually, because I don't know if this particular reaction that we're throwing out is first order or second order. Those would change the units there. But there we go. So this is a very fast reaction. Super duper fast. A trillion whatever's per second. Awesome. So there we have it. That is how we can see the temperature dependence on our reactions, our rates of reactions. So, wow. We are going to spend the rest of this week, by the way, still doing kinetics. So, like, technically we're going to, like, kind of finish the stuff maybe today, maybe tomorrow. And then we're going to just spend the rest of the time doing problems, just because some of these problems can be super, super long. And so I want to make sure that we have enough time to really go over them in detail, just because there's so much math, so many steps required for all of these. So, yeah. Any questions on that one? Okay, well, in that case, let's take a look at reaction mechanisms now. And so, again, I kind of hinted at when we started this chapter that rate laws will give us info about the mechanism of a reaction. And so we're going to see that some reactions are kind of one step and they're done. You know, there's not really a problem there. You know, here's a just one-step reaction. We don't care about one-step reactions. We're going to see, however, with multi-step, I don't know how to spell. With multi-step reactions, remember we can end up getting intermediates, right? I didn't mean for that to be the same energy, but who cares? Or, you know, we could have, you know, a three-step reaction or something, where we would end up having all these humps. And we're going to see that we have different activation energies for each one, right? But that aside, we can look at kind of, we're going to be able to look at reaction mechanisms to kind of figure out what they look like in terms of like what's actually going on. So the reaction mechanisms are going to give us kind of hints as to what this sort of graph would look like. For example, we're going to see that this one, this particular graph, would correspond with a two-step reaction with what we're going to see would be the second step is the slow step. We're going to be able to look at reactions and be able to come up with information like this, and we'll be able to throw out a graph like this. If we were to look at this one, we would see that this is a three-step reaction, and we're going to see that the first step is slow. And so we're going to see what all this is related to. These are kind of just kind of hints as to what sort of things we're going to see here. And just to reiterate one more thing, we're going to see, or we saw that previously the rate law does not necessarily mean the same thing as your overall reaction. For example, I think we had a rate law like this where we were looking at the reaction of NO2 plus carbon monoxide. They transfer an oxygen, right? We saw that this rate law didn't really have anything to do with this overall reaction, right? There's no obvious kind of way to go from, hey, here's this rate law, to here, look at this overall reaction. But we're going to see that just like we did with Hess's law, overall reactions can be broken up into multiple steps, right? Overall reactions can contain multiple steps. And what's important here in purple, because purple means important, I guess, we're going to see that step reactions will always correspond with rate laws. And so we're going to see here that if rate equals that we must have something. This tells us that our slow step of the reaction, or rather the rate determining step, must be 2NO2 go to something else. Where that would be your coefficient. So in an overall reaction, the coefficient does not correspond with the rate law. It can, but it does not have to. However, in step reactions, we're going to see that the coefficient will always be the same as the exponent. So if we saw experimentally that a particular reaction was second order in respect to NO2, some step in that reaction has to include 2 NO2 molecules. And that particular step is always the slow step. We'll get into slow and fast. Actually, we should probably talk about that now. I'm getting excited here. I'm getting ahead of myself. If a reaction has multiple steps, the slow step determines the rate. Consider you are at this mythical place called an airport. I know airports do not exist in the COVID era, but back in the day, airports were this place where you would go to wait in line at the security checkpoint. That's kind of the biggest point of going there, right? You'd have all these people walking around going crazy. Then they all line up for security and wait there for an hour. Yes, before the dark times, right? Before the dark times. Where everyone would wait in the security line. And then once you got through the security line, you are wondering about going to your gate. So for example, here's a reaction. Person from car to person on plane. Can I draw a plane? No. I guess there's it's a fish. That's a plane. I don't know how to draw a plane. Anyways, here's our overall reaction. But it turns out that there are actual steps associated with this, where we have person in car going to person waiting in line, which then goes to person on plane. And we're going to see that in this particular example that I've done, this is the slow part here, where we're waiting in line. So while we transition from going in line to going to the plane, that's slow. This one would be fast. We can get in line real quickly. But to get through that line, to get past that step, that's what takes time. And so, no one cares about going from the car to wait in security line. Like, That doesn't take any time at all. There's really no hold up to that. Everything at the airport determines how long your security checkpoint is. And so we're going to see that is going to be this slow step. That's going to determine how much time you need to be, at the airport before your plane takes off. And so that's kind of what this means here, is that you can arrive with as much time as you want beforehand, but it all depends on that line here. So anyways, that's going to be what's called the rate determining step. And that's going to be the one that's going to determine the rate law for this reaction. So our rate would be K times whatever, the people. So that's what it would be there, whatever that reaction happens to be. So let's look at it and see if we can kind of look at a set of proposed reactions to make this kind of thing work. So let's look at our NO2 plus carbon monoxide turns into these things. And experimentally we saw that the rate was that. Yes, it is, Star-Lord. Absolutely. Your slowest step is the one that will determine your rate. Okay. So, if we're to just say, okay, it just happens like this, if we just say scenario 1, it's just that reaction, there's nothing else that happens here, we would expect that the rate is equal to K times we would expect that for our rate law if it were just that one-step reaction. However, because it is not, that tells us there are multiple steps going on here. And so I'm going to propose one to you. I'm going to say, well, hey, how about if we do this thing? Let's go ahead and say that the first step is actually breaking NO2 into NO and O. And let's say that what else shall we have? That the oxygen might do something like this. If we were to look at this reaction, if we were to add these up, remember, just like with Hess's law, if we add reactions up, we do end up with NO2 plus CO turns into CO2 plus NO, right? We see that the oxygen will cancel out, that one oxygen. If we're to look at these two particular steps, if we say, okay, we would say it's take K times NO2. Let's go ahead and look at the other one. If we look at this reaction, it would be K times oxygen times carbon monoxide. However, neither of these agrees with our reaction, does it? Or our experimental data. We found that it was KNO squared, NO2 squared. So this is probably not a good mechanism. Neither of our particular reactions here would give us the correct rate law. So let's think of another one. How about if we do it this way? That might work. And then if we say, okay, I'm going to take these guys and put them together, and we get 2 carbon dioxides. Let's look at what the rate laws for these would be. If we add this stuff up, we're still going to get the same thing, right? We get 2NO2 plus 2CO turns into 2NO plus 2CO2, which we would then just get rid of all those pesky 2s, right? We don't care about those in our reaction. So overall, we would still get our overall reaction. But now look at what's happening here. Aha! And if we were to do this, we can do that, by the way. We saw our experimental evidence came up with that as our rate law. And so it would seem that this mechanism that is proposed, so someone said, hey, I was thinking about it, maybe this is what's happening in here. This particular mechanism that we've written out here does have a step that corresponds with our experimental rate law. And so we just kind of discussed that the slow step is what determines our rate here. And so if that's our rate law, then this could be what's happening. And it turns out that this would be the slow step in that case. So with these, I'm not going to be asking you to kind of come up with mechanisms. We're kind of just going to be evaluating mechanisms and say, hey, does this fit the data that we're given? We'll go into it more, but this tells us overall that if this was our mechanism, we would have the slow step be that first step, and our second step would be a faster one. And so we would say, okay, if we were to kind of look at this thing graphically speaking, I'm just putting this as exothermic. I don't actually know if it is or not. But that's telling us, hey, here's our first step. Here's our second step in that. And note, we also have an intermediate. We have that lovely dioxygen there. And so this is the whole point of doing all this stuff is we were able to rule out this first mechanism. We were able to say, well, it's not just nitrogen dioxide breaking into nitrogen monoxide and an oxygen atom. That's probably not happening here because our rate evidence doesn't agree with that. But however, we do have a mechanism that could be possible that would agree with our kinetics data that suggests that our intermediate is actually O2 and not just a singular oxygen atom. And so through this, we're kind of able to, I want to say just kind of rule things out. I mean, we can rule things out, but we get more information about what's actually happening here. So our reaction is not as basic as this overall reaction. We're just throwing an oxygen atom around. We're actually potentially forming O2 in the middle of the reaction and then using that O2 immediately to oxidize carbon monoxide. Oz is doing that sort of thing. Relax, buddy. And so by kind of making sure that our rate law agrees with our mechanism is going to be important. So that's kind of the whole point of doing all this crap. is to now figure out that maybe in this reaction we're using dioxygen and not a single oxygen atom. Seems like a ton of information and work just for something that may or may not be, as exciting, let's just say. But it definitely is exciting. The more information we have, the more we can do with it. So, yeah, I would say so, because it's going to react as soon as it is produced, for sure. And so you can see here that the hump for the second one is going to be lower than the hump for the first one as a result. So kind of as soon as we come over that first hump, we're good. We're good to go. We just keep on rolling and we're done. Notice that oxygen is an intermediate, not a transition state. Remember, intermediates can be stable and isolated. We could capture that oxygen if we wanted, if we had some way of controlling this reaction and we were to kind of isolate oxygen, we would have more evidence that this would be our reaction mechanism, right? A transition state would be something like where we have I have too many bonds there, don't I? Maybe where this particular bond is elonging or something. A transition state would be where we're kind of like breaking the bond or something. It's not something that we can isolate. Remember, transition states are something that we can't isolate. They're not stable. They are, energetically very high. That's why they're at the highest point on this graph. We can't isolate it, and it would just either go back down to where it started, or it would continue on in the reaction. So transition states would be something that can't be isolated. It's kind of halfway through reacting. And so if we can isolate, if we do the reaction, at reasonable temperatures or something, and we're able to isolate O2, that would give us more information that our reaction mechanism is indeed what's happening here. So that's kind of the whole point, is we kind of piece together as much information as we can to get as much insight into how reactions are taking place, because we're going to see that's the whole point of doing this chemistry, is how do we get reactions to take place that we want to happen. And so the more we know, the more tools we have, better off we are. Ooh, I feel like I was on my soapbox there for a while. So, wow, all this fun stuff. We're going to continue with this tomorrow. We're going to look at a case where we have the slow step as the second step. And we're going to get through a bit of terminology that I had kind of forgotten to go over today. So we'll talk about that in terms of these mechanisms. We'll go over some more complex mechanisms. We'll talk about catalysis tomorrow and half-life, and then we'll just practice for the rest of the week. So it'll be fun. And we'll go over Excel tomorrow as well, I think. Alrighty, well, with that, exciting stuff. I think Lovepreet wanted homework, so I'm going to have to look and give us some homework. You can go ahead and blame them for it, not me. And I think Jackson wanted 43 problems, so I'll try and do my best to get that many for you guys. So we'll have fun. Alrighty, well, take care. See you tomorrow. Have fun. I don't want to grade 43 problems. Forget it. All right, see you guys.